Hello students, welcome back. This is the second lecture of Module 3, where we are now working towards our goal of being able to compute the solar radiation that is incident upon a solar panel, so we know how much electricity it can produce and so on. In this part of the lecture, we're going to be learning about solar declination. Now, let's make sure that we're clear about this. We've encountered this term actually both in the first and the second module as well, but this is the first time that we're going to be working with it in a more mathematical sort of way and so on. Solar declination, remember, is the latitude at which the sun will be directly overhead at local noon. And the symbol that we're going to be using for solar declination in this class is delta S. That is a lowercase delta, that little squiggly sort of thing up there. So delta S will be our symbol for the latitude of the solar declination. It'll be a positive number if it's in the northern hemisphere. It'll be a negative number if it's in the southern hemisphere. It'll be 0 if it's at the equator. We can work with it in terms of degrees, like degrees latitude, or for a lot of the calculations it's going to be useful to convert it to radians. So what's actually going to happen in this lecture, let me tell you that I love these pictures that are in the background. These are different pictures I found online of people who had snapped the picture of their shadow at noon if they were at the location of the solar declination. And so their shadow is just right down there by the feet because the sun is directly overhead at this time. So it kind of almost looks like they're standing, on a puddle or something, but they're actually standing on their shadows because the sun is directly overhead at this time. What's going to happen here in this lecture is we're going to be computing the solar declination given a day of the year. I mean, you did something similar to this in the first module of the course when you were just using an Analemma, but the diagram that can be used to estimate the solar declination, but we're going to do a better job of it. But first I want to kind of illustrate how the solar declination changes over the course of the year, and I'll confess that I just swiped these slides from the Intro to Meteorology course because they spend some time on this idea too, and these illustrations are better than anything I could draw. If we think about the orbit of the Earth, and how the Earth's axis is tilted on different days of the year. Remember, the Earth's axis is always tilted and pointed in the same general direction, out towards Polaris, the North Star. But as we go around the sun, then that means the Earth is actually pointing in slightly different direction. The northern hemisphere is tilted towards the sun at some times of the year. The northern hemisphere is tilted away from the sun on different times of the year. If we just took, for example, the June solstice, which is June 21st or June 22nd, and thought about like how one half of the globe is illuminated and the other half of the globe is in darkness as the Earth rotates. If I drew three little people there on the globe here and put some rays from the sun encountering them, clearly each of those people are getting some sunlight, but only the yellow person is actually having the sun directly on the top of his head. His shadow is right there by his feet. He is the one who is at the solar declination at that time, and if I highlight the latitude line that he is at this time, that is the solar declination, the latitude at which at noon the sun will be directly overhead. That person is standing at the subsolar point in this particular example. The solar declination is the latitude of the subsolar point. In the same sort of way, we could reflect upon the whole orbit of the Earth and as it goes around the sun and say, switch over here to the December solstice. This is roughly December 21st or 22nd, depending on leap year and so on. Again, we see we have an illuminated side of the globe and a dark side of the globe as the Earth rotates on its tilted axis. And again, if I put three little people there on the globe at different locations, each of those three people are experiencing sunlight, but only the yellow person there is actually having the rays of sunlight directly on the top of his head. At local noon, that person is at the subsolar point. He is at the solar declination. His latitude is the solar declination, and if I highlight the latitude line that person is on, we can see that that is the solar declination on that day. It happens on December 21st to be the Tropic of Capricorn, which is 23.5 degrees south. 23.45 degrees south to be a little bit more strict about it, but 23.5 is close enough. So let's actually find a mathematical way to come up with the solar declination. And again, for the textbook that I used, it turned out to be not terribly difficult. The solar declination is just equal to all that stuff over there on the right-hand side. Writing a little octave code that can do this is probably going to take you 1 or 2 lines of code. It's not going to be that big of a deal. Just to look here at the kinds of terms that are going into this here, we got this phi r. Phi r is the symbol that the book was using, that I got these notes from, this idea from, to give the tilt of the Earth's axis with respect to the plane of the ecliptic, the plane that is the solar system, through the Earth's center and the sun's center and so on. The Earth is tilted 23.5 degrees, more specifically 23.45 degrees. if we switch over here, that C is just 2 pi radians or 360 degrees, depending on whether your calculator or octave or whatever is what you're using. Octave only works in radians, so you would want to use that as being 2 pi radians. That P here is going to be the period of the Earth's orbit. Use 365.25 days. If you were doing it so that T and TR are going to be dates, so you're probably going to use this in terms of days, so you're going to have your P is going to be, as long as the units cancel, it's fine. So if P is in days and T is in days, it's fine. If for whatever reason you wanted to know this more accurately than just a day, like if you wanted to know the solar declination at a particular minute or something, you would have to do it in minutes then, or seconds, or whatever. Don't do that. Days are close enough. T is going to be the time since the start of the year, and TR is going to be the date for June 22nd. So, like, probably you're going to do this in Julian days. So T would be the Julian date that you're working on, and TR would be the Julian date of June 22nd, which I think is 173. But obviously look it up on a table or make yourself a little spreadsheet or whatever it takes to make that work. So if you do this calculation and you just made a little graph, I mean, I like this little graph right here that just shows how over the course of the year, the solar declination varies from 23.45 degrees south, that's the Tropic of Capricorn, up to, in June, at the summer solstice, it goes up to 23.5 degrees north, 23.45 degrees north, which is the Tropic of Cancer. And you can see how on the equinoxes, in March and in September, the solar declination is right at the equator itself. Pretty straightforward, simple little diagram here. Another way to display that same curve is to plot it as the Analemma. Now on the Analemma, we don't use the x-axis for anything for this kind of application, but on the y-axis, remember, you use the Analemma as sort of a calendar. You followed it around to the date that you are talking about, and then you read over to the y-axis to find out the solar declination. Again, it's just an approximation, but it maybe can help you check your work when you're writing a program. Am I getting a realistic answer for the solar declination? Or just Google it. Or go to wolframalpha.com. Put in what is the solar declination on the date that you're doing, and it'll check your work for you. I recommend doing that kind of stuff. The project is hard enough. Find out if things are working. Alright, before we move on to part 3 of this lecture, we want to start thinking about, and I want you to answer a couple quick questions. They're fairly simple this time. Question 4, what is the symbol, this is continuing the question numbers from the previous lecture. Question 4, I was asking in this lecture, what is the symbol for the solar declination? S naught, delta S, VR, or TR? Alright, so make up your mind as to your answer, follow one of the 4 links below, and we'll get a little feedback before we move on to question 5.